So, how do we actually figure out the absolute best way to get to 100% renewable energy? I mean, it's far more complex than just installing a whole load of solar panels and wind turbines, isn't it? We're talking about navigating these, incredibly intricate systems, building massive new infrastructure, and solving these, well, mind-boggling economic equations, often on a global scale. It's just a monumental challenge, really is. And that's precisely where today's deep dive comes in. We're going to unpack a truly fascinating study. It takes a magnifying glass to the very tools we rely on to model our energy future. We're diving into impacts of model structure, framework, and flexibility on perspectives of 100% renewable energy transition decision-making. Quite a mouthful, but important. Our mission today is really to cut through that considerable complexity. We want to extract the most important insights so you walk away truly well-informed. Informed about the subtle yet profoundly powerful ways different modeling approaches can shape our path to a sustainable future. It's about understanding the map itself. Not just the destination.
Okay, so with that monumental challenge in mind, achieving 100% renewables, let's look at the sheer scale of the research pouring into this. The climate crisis has clearly fueled an incredible surge. I mean, research focused specifically on 100% renewable energy systems. We're talking an explosion from just over, 10 articles published per year back in 2011 to a staggering 550 by mid-2021. That's a massive acceleration of focus and urgency.
Yeah, it really is. And what's particularly insightful here, I think, is that energy system models, or ESMs as they're often called, they are absolutely central to this accelerating research. They're designed with a really vital purpose, which is to demonstrate the technical feasibility and, critically, the economic viability of these fully sustainable, sector-coupled energy systems.
Sector-coupled, meaning connecting electricity, heat, transport, all of it together.
Exactly, all those pieces. But, and this is what the study really digs into, while their fundamental purpose is consistent across different research groups, their internal characteristics, the assumptions baked in, well, they can vary widely. And that variation, as we'll see, can severely affect the structure and the outlook of 100% renewable energy solutions.
Oh, okay.
It's like building a bridge, right? You want it to cross the river, but the actual blueprints, the engineering details can look very different depending on who draws them up.
Right. Different blueprints for the same goal.
Yeah.
So these models are indispensable then. They help us visualize, plan. They also come with pretty significant challenges. Things like ensuring complete transparency of all the assumptions built into them. That's huge.
Absolutely.
Or optimizing these incredibly complex interconnected systems across all those diverse sectors, power, industry, transport, plus capturing all the nuanced techno-economic details that, change from one place to another. And this study courageously takes on that very challenge. It does it by directly comparing two of the most widely used ESMs out there, EnergyPLAN and the LUT Energy System Transition Model.
Yeah, and that's a really crucial distinction you've made there between the two. EnergyPLAN, which was introduced way back in 2006, it's primarily what we call a simulation tool.
Simulation.
Yeah.
Okay.
Yeah, think of it like a highly sophisticated calculator. You, the user, you manually define all the inputs, how much solar, how much wind, what kind of storage, and then the model simulates how that system would actually operate. You iterate, repeat the process, adjusting inputs until you find a solution that looks, optimal to you.
So it's more hands-on, like trying different routes on a map yourself.
Exactly. You're drawing the paths. The LUT model, on the other hand, launched more recently, 2015, it operates fundamentally differently. It's an optimization model.
Optimization, got it.
So instead of you manually trying different combinations, it uses linear optimization techniques. It determines the least cost energy system under a set of predefined constraints, things like emissions targets or resource availability.
So it finds the best path for you.
Precisely. It's built to find that optimal path automatically. More like a GTS that instantly calculates the absolute fastest route based on all the data it has.
Okay.
And this difference in fundamental approach, simulation versus optimization, is really key to understanding the results they found.
And these aren't like obscure tools only a few people use.
Not at all. This study notes EnergyPLAN has been cited in 73 published articles and the LUT model in 63.
Wow.
That makes them by far the most frequently applied models specifically for 100% renewable energy scenarios. They really dominate the field.
Which makes this comparison incredibly valuable then.
Hugely valuable. So this study set out to compare these two powerful models by developing cost-optimal scenarios. But under identical assumptions, that was critical, for a specific case country, Bolivia.
Bolivia. Why Bolivia specifically?
Well, several compelling reasons. Firstly, it's a Sun Belt country, meaning it has incredibly rich solar resources, which makes it a really interesting candidate for 100% renewables.
Makes sense. Lots of sun.
Right. And critically, Bolivia is also part of the Global South, a region that has historically been significantly underrepresented in these kinds of energy system analyses, despite often having immense renewable potential.
That's a really important point.
It is. And finally, Bolivia currently lacks defined renewable energy targets, which made it an ideal sort of blank slate or template for analysis. It allowed the researchers to explore scenarios without, predefined policy biases pushing them towards certain outcomes already.
It is a thoughtful choice.
Yeah.
Okay, so they picked Bolivia. How did they structure the comparison? What kind of scenarios did they run?
Well, the study explored different modeling approaches, adding layers of complexity to see how the models handled them. First, they looked at overnight scenarios. This is essentially imagining a brand new 100% RE system by 2050, completely ignoring any existing infrastructure, like designing from scratch.
A clean sheet of paper approach.
Exactly. Then, to bring in a dose of reality, they did transition scenarios. These are much more realistic, right? Mapping a gradual pathway from the present energy system to that 100% renewable future, and carefully accounting for existing legacy systems, like old power plants, existing grids, and how they'd be integrated or phased out.
Right. This is where you see maybe the truer cost and complexity of the transformation. Yeah, rather than a theoretical ideal. And finally, they explored geographical resolution. They ran single-node scenarios, modeling Bolivia as just one aggregated region, one big energy hub.
Okay.
Then they contrasted that with multi-node scenarios, dividing Bolivia into 8 distinct subregions.
Ah, much more detailed.
Yeah, allowing for detailed geographical analysis, testing grid interconnections,
Mm-hmm.
seeing if that spatial detail actually changed the outcome for things like transmission needs. Did more detail mean a different optimal solution?
And what's really fascinating here is how the internal mechanics, the fundamental design of these models, handles different aspects, even subtle ones, and how those differences force the researchers to make some really careful adjustments to ensure a fair comparison.
Like what specifically?
We'll take heat classification, for instance. The LUT model, it precisely categorizes heat demand by temperature high, medium, low, which directly impacts how efficiently that heat can be supplied by renewables like heat pumps or solar thermal.
Okay, different temperatures need different solutions.
Exactly. EnergyPLAN, on the other hand, uses different district heating groups, which aren't always interoperable in the same granular way. So this study actually had to adjust EnergyPLAN quite significantly to align with LUT's more granular approach, just to ensure an apples-to-apples comparison on how heat demand gets met.
A lot of work just to get them aligned there.
Definitely. Then there's electricity storage. The LUT model explicitly includes a whole range of storage tech batteries, pumped hydro, compressed air, and it can optimize for the best mix.
The toolbox approach.
Right. EnergyPLAN, at least in the version used for this study, it treated electricity storage as one aggregate option, like one big generic battery. So this required some careful, manual modeling to simulate specific battery costs within that aggregate framework, just to try and match LUT's capabilities.
Like trying to use an adjustable wrench for every job instead of the specific socket size.
That's a good analogy, yeah. You can get it done, but maybe not as perfectly optimized.
Okay, what else?
And for synthetic fuels, things like renewable diesel or jet fuel made from electricity, the LUT model uses advanced Fischer-Tropsch processes for this power-to-fuel conversion. It's essentially a highly efficient chemical route.
Right.
EnergyPLAN, however, used a power-to-gas to liquid, or MIDI-GTL route. First electricity to gas, then gas to liquid.
More steps.
More steps, and generally less efficient than the direct Fischer-Tropsch. So this meant significant adjustments to cost and efficiencies in EnergyPLAN were needed for a truly fair comparison of those fuel production pathways.
Okay, so heat, storage, fuels, anything else major?
Well, they even looked at the seemingly small, almost pedantic detail of how heating values are handled.
Heating values, like HHV versus LHV.
Exactly. Higher heating value versus lower heating value. Without getting too bogged down, it's about whether you account for the energy released when water vapor condenses during combustion or conversion. For synthetic fuels, where water is often part of the process, using inconsistent values, even by a tiny bit, can subtly but significantly change the energy balance, and therefore the calculated efficiency and cost. It's a tiny detail, but it has real financial implications they had to meticulously align.
Wow, that is meticulous. Okay, so after all that incredibly careful setup, all that alignment, adjusting assumptions. What does it all mean for Bolivia's path to 100% RE? Did these two leading models, given the same data, same rules, finally agree?
Well, across all the scenarios in the study, the answer regarding the type of energy system was remarkably clear.
Okay.
A future energy system overwhelmingly dominated by solar PV,
Oh.
which is fantastic news for Sunbelt countries like Bolivia, right?
Yeah.
Given their excellent solar resources. The overall energy structure for a fully renewable system really converged on solar power. That's a very encouraging, consistent signal.
That is consistent. However, and this is a big however, while the energy structure converged on solar, the costs revealed very significant differences between the two models.
Oh, how different. When comparing those single-node overnight scenarios, the simpler ones, BPS, EP for EnergyPLAN, and BPSS for LUT, EnergyPLAN showed noticeably higher annualized costs.
How much higher?
Specifically, about 25% higher than the LUT model.
25%. That's not noise. That's a huge difference.
It's a massive difference.
So why? Why the discrepancy if the underlying assumptions were, as you said, painstakingly aligned? What's going on inside the models?
That's the crucial question, isn't it? And the study found compelling answers. EnergyPLAN's higher costs were largely attributed to two main factors. First, it had fewer avenues within its framework for comprehensive electrification, especially in the heat sector.
Less direct electric heating.
Right, which led to increased use of synthetic natural gas, SNG, to meet heat demands where direct electrification, modeled in LUT, would have been more efficient and cheaper.
Okay, so more expensive fuel needed. What was the second factor?
The second was a much larger required methanation capacity, that's the process to make the SNG, due to EnergyPLAN's operational schema for how it produces SNG. It ties SNG production directly to something called critical excess electricity production.
Excess electricity. Stuff that's generated but not immediately used or stored?
Exactly. Electricity that in some systems might otherwise be curtailed or wasted. LUT's framework, being an optimization model, was just more flexible. It allowed for a much more efficient utilization of all its components, better integration across sectors, leading to significantly lower overall costs. It could avoid that wasted excess and enable more direct electrification where it made sense.
So the optimization model found cheaper ways by using everything more efficiently. That makes sense. Now here's where I thought it got really interesting. The impact of that geographical detail, the single versus multi-node comparison. And transmission.
Yes.
For a country like Bolivia, with abundant, widely distributed solar resources everywhere, the multi-node scenarios in this study revealed little benefit from highly interconnected power transmission.
Right.
Yeah. Sending power from the regions with the absolute best solar across the country added little value or cost savings compared to more decentralized systems, where power is generated and consumed more locally within those subregions.
That's fascinating, and it really differs sharply from what we often see modeled for places like Europe, doesn't it?
Exactly.
Where you have these large spatial disparities, lots of wind maybe up north, lots of solar down south, making extensive interregional transmission seem really economically beneficial, almost necessary for balancing.
Right.
But for Sunbelt countries like Bolivia, this study suggests something different, that a highly decentralized system, maybe with a backbone of solar PV, batteries, and electrolyzers for local balancing or fuel, it doesn't necessarily require massive, expensive, long-distance grid infrastructure for balancing supply and demand.
Which really strengthens the argument for regional energy autonomy, doesn't it?
It does. It has profound implications for energy policy, for security, especially maybe in many developing nations. More localized solutions might be more cost-effective.
Okay, one more key comparison. That overnight clean slate vision versus the realistic transition pathway. How did those stack up on cost?
Ah, yes. Connecting this back to the bigger picture for actual decision makers. This study demonstrated a really important point here. Those overnight scenarios, the ones ignoring existing infrastructure.
The clean sheet design?
Yeah. They undershoot both the levelized cost of electricity, LCOE, and the total annualized costs by a significant margin. We're talking 20–30% lower.
Lower than the transition scenarios.
Exactly. 20–30% lower than the more realistic transition scenarios that properly account for the legacy energy system and the gradual changeover.
Wow. So ignoring what's already there makes the future look significantly cheaper than it likely will be.
Precisely. It's a crucial finding because it highlights that ignoring existing assets like old power plants that still have life or grids that need upgrades, not replacement, and just the gradual nature of change, it can significantly underrepresent the true practical costs of an energy transition. You can't just wish away the present reality when planning.
That is a critical takeaway for anyone making policy or investment decisions. So this deep dive into impacts of model structure, framework, and flexibility on perspectives of 100% renewable energy transition decision-making. It really shows us that while the big picture, like that solar-dominated future for Bolivia, seems consistent across models, the devil is absolutely in the meticulous details of how those models are built and what they can actually optimize for.
Exactly right. It's not just what the models tell us, but how they arrive at those answers. The study really highlighted that inherent limitations in a model's design, its structure, can prevent it from reaching the truly cost-optimized solution. Particularly, as we saw, regarding comprehensive electrification of heat and efficient synthetic fuel production routes. And it also underscored the importance of those incredibly meticulous details, like the consistent heating value assumptions. Things that might seem minor, but as we saw, can impact annualized costs by a non-trivial 2–4%. Every detail matters in systems this vast and complex.
It sounds like this kind of rigorous analysis comparing the tools themselves is just getting started.
I think so. The study itself suggests that these direct head-to-head comparisons of widely used ESMs offer incredibly valuable insights, and it recommends further cross-validation, comparing these results with other prominent models like PyPSA, Remix, Times.
To check in the work, basically.
Exactly. Keep refining our understanding, building greater confidence in the projections that guide our path forward. It's a continuous process of learning and refinement.
Ultimately, this deep dive reminds us, doesn't it, that planning for our 100% renewable future isn't just about the technologies we choose to deploy, but it's also critically about the very tools, the models we use to simulate and predict that future, understanding the profound strengths and sometimes the subtle but important limitations of energy system models. As explored so thoroughly in impacts of model structure, framework, and flexibility on perspectives of 100% renewable energy transition decision-making, well, it's absolutely critical for making truly informed, effective, and cost-efficient decisions. So the thought to leave you with is this. What opportunities might we miss? Or perhaps more worryingly, what costs might we significantly misestimate? If we don't truly understand the inner workings, the assumptions, and the limitations of the models guiding our journey to 100% renewable energy. Keep that thought with you until our next deep dive.